Hello guys, welcome to Quality and Welding Methodology. Today discussing on Postweld Heat Treatment PWHT of chromium molybdenum piping and tubing part 2 as per American Welding Society. Postweld Heat Treatment PWHT. General, the primary benefit derived from PWHT are following. First, stress relieving. Second, tempering or softening and restoring ductility. Third, diffusing hydrogen. A combination of this can reduce the risks of cracking, improve mechanical properties, and provide better corrosion resistance. Suggested PWHT temperature for various base metals are listed in Table 4. For joining in involving several materials, the temperature for the highest alloyed chromium molybdenum steel are used, selected. PWHT temperature, the temperature range listed in table 4 are broad in order to accommodate different need for different industry. Other and at times more restrictive PWHT temperature have been accepted on the basis of code requirement, welding procedure qualification and service experience. For instance, when normalized and tempered steel are used, the PWHT temperature should be lower than the tempering temperature. When high creep and rupture strength are the primary concern, as in the power industry, the temperatures selected for often at the lower end of the range. However, when resistance to corrosion and hydrogen embrittlement are the primary concern, as in petroleum and chemical industry, temperature at the higher end of the range are often used. Holding time. Most holding time required holding time at the specified temperature of 1 hour per inch of thickness 25 mm. Thumb rule in 1 inch per 1 hour. But they differ considerably regarding the minimum time at temperature for chromium molybdenum steel. ASME B31.1 required only 50 minutes and ASME B31.3 required 120 minutes. For thin material, it's likely only for 15 minutes. For 15 minutes to relieve an adequate amount of residual stress, which is primary concern of ASME B31.1. However, it takes longer to temper the material and proved satisfactory concern resistance, which is usually a primary consideration for ASME B31.3 fabrication. The latter is special interested for chromium molybdenum steel exceeding 4% chromium. Suggested PWHT temperature range showing here. Heating and cooling continue. Heating and cooling requirement also differ considerably, while there is generally agreement that heating should be uniform. Only ASME B31.1 specifies as maximum heating rate of 600 degree Fahrenheit per hour for up to 2 inch 50 mm thick pipe. However, pipe built to ASME B31.3 has performed successfully when heated from ambient to PWHT temperature in few minutes. Heating and cooling. Cooling requirement also differ considerably, but there is generally agreement that the cooling should be uniform to minimize the re-establishment of residual stress. While ASME B31.3 does not list or spell out any numerical requirement, ASME B31.1 specific a maximum cooling rate of 600 degree Fahrenheit per hour for thickness up to 2 inch 50 mm pipe. This has been accepted red chromium molybdenum steel and extend holding time. A slower cooling rate or both may needed to meet specific hardness requirement. It is advisable to use the welding procedure qualification to determine the adequacy at the specific holding time and cooling rate. Local PWHT. The above requirement can easily be met when the entire pipe or tubing assembly is Postweld heat treated in a furnace. Since this often is not possible, local PWHT represent an acceptable alternative. The method and the equipment for heating should be provide uniform heating around the circumference. If branch connections are Postweld heat treated, care should be taken to heat a wide band of metal around the pipe or tube into which the branch is welded. Otherwise, local expansion and permanent upsetting may leave the heat area with higher and more extensive stress than those present in the as well structure. For local heat treatment, a circumferential bend around the pipe should be heated to the specific temperature range. The heating and bend shall be straddle the center line of the butt, nozzle or attachment joint. Figure 1 illustrate the minimum width of the bend which, according to the two most requirements specified American piping code, must be heated to the PWHT temperature. While they did not have identical requirements, both appear to provide satisfactory result and either can be followed from non-code application. To produce satisfactory result, the temperature should be gradually diminish outside the heated band. This is usually achieved by extending heating element and the insulation beyond this band. For a detailed discussion of local PWHT, please refer to ANSI AWS D10.10 recommended practice for local heating of welds in piping and tubing. ASME B31.1 and B31.3 bandwidth requirement for local PWHT. Quality Control PWHT. Adequacy of any production PWHT operation involving chromium molybdenum steel can be established by carefully monitoring properly installed thermocouple. The Postweld Heat Treatment weldment can also be inspected by hardness testing. A wide range of portable instrument is available. When using such instrument, it is important to inspect not only the weld deposit but also the HAZE heat affected zone. For the material covered by these documents, the hardness number drop after PWHT. The specific changes in hardness depends upon the individual alloy and the applied PWH cycle. Some code like ASME B31.3 and some job specification dealing with corrosive service, especially maximum hardness limit. For other applications, the ability of pass the bend test associated with the procedural qualification demonstrate adequate ductility. Repair and maintenance welding of service exposed chromium and molybdenum piping and tubing. While this section is not intended to review all possible repair and maintenance options, three subjects related primarily to chromium molybdenum piping and tubing should be considered. Base metal contamination, cleaning metal surface prior to welding on any new or used material applied to all metal. However, chromium molybdenum steel has been in high temperature hydrogen service may have absorbed some hydrogen. When welding over such contaminated steel, the heat associated with any welding process can diffuse some of the hydrogen. If this hydrogen enters the newly deposited weld metal, it is likely to cause porosity and even cracking. Often the weld, especially when using the GTAW process, can see this gas bubble in the weld puddle. This problem can be overcome by heating the steel for about 50 to 30 minutes prior to welding. While optimum holding time and temperature have not been established, present recommendation range from 400 to 1200 degree Fahrenheit 200 to 650 degree centigrade. A test weld or a bend on the bevel face using the GTAW process may demonstrate the weldability of service exposed steel. Temper embrittlement. Some chromium moly steel can embrittle when exposed to elevated temperature for an extended time. The loss of ductility at ambient temperature, which is known as temper embrittlement, has been experienced primarily in 2/4 chromium molybdenum steel, which had operated for many months about 850 degree Fahrenheit, 450 degrees centigrade. Since this embrittled steel had an expectable ductility at a typical preheat temperature of 300 degree Fahrenheit, 150 degrees centigrade. Temper embrittlement does not normally present weld problem. However, this low ductility can be problem when pressure testing or pressurizing the piping system at lower temperature. Relaxation of PWHT requirement. Relaxation PW while new chromium moly steel fabrication and construction often require full furnace for full encirclement. PWHT as described in 6.4. Several inspection type code have provide some relaxation when repairing, modifying chromium molybdenum piping and tubing system. The following document provide some relaxation and at the same time impose several control and limitation for which the specific document should be consulted. API 750 permits spot heating of weld area in place of heating circumferential bend around the pipe and nozzle. Second, ASME B313 permitted the substitution of higher preheat temperature, post heating and tempered welding, post heating and tempered welding as an alternative to PWHT of carbon and low alloy steel. However, due to lack of experimental data, care should be exercised when applying the alternative method to chromium moly steel while more than 2.5% chromium. Spot PWHT can achieve the same reduction in hardness as conventional PWHT. Temper hardening can also soften the weldment, but the adequacy of the procedure must be demonstrated. However, neither system can be expected to appreciably lower any welding related residual stress. There is some concern that the API method may increase distortion and residual stress in the longitudinal direction. Thank you.